Welcome to my channel, and today we will discuss some another definition of modern algebra. So there's another definition: if G is a group and A comma B belongs to G, then the element A, B, A inverse, B inverse is called the commutator element of A comma B, and the set of all such commutator element is denoted by U is equal to A, B, A inverse, B inverse, such that A comma B belongs to G. If G dash is a subgroup of G generated by U and is a smallest subgroup of G. Now there is another theorem: G dash is a normal subgroup of G where G dash denotes subgroup of G which is generated by U. इसका प्रूफ देखते हैं. A comma B belongs to G, so A, B, A dash, B dash belong to G dash. If there is another element, if C belongs to G dash, then if C belongs to G dash, then AC A inverse is equal to A C A inverse dot E. ए सी ए इन्वर्स ई को लिख सकते हैं हम सी इन्वर्स सी. सो ए सी ए इन्वर्स सी बिलोंग्स टू जी डैश. सिंस ए सी ए इन्वर्स बिलोंग्स टू जी डैश, hence G dash is a normal subgroup of G, or the commutator subgroup is a normal subgroup of G, hence proved. Now there is another theorem: prove that G dash is a abelian. इसका प्रूफ देखते हैं. सिंस G डैश इज़ अ कम्यूटेटर सब ग्रुप ऑफ G, एंड सो बाय थ्योरम G डैश इज़ अ नॉर्मल सब ग्रुप ऑफ G, एंड बाय द थ्योरम G इज़ अ ग्रुप and N is a normal subgroup, then G by N is a quotient group since G by G dash is a group. If A comma B belongs to G, then A, B, A dash, B, A inverse, B inverse belongs to U. But U is a subset of G dash, and thus A, B, A inverse, B inverse belongs to G dash. Then by the theorem G dash A, B, A inverse, B inverse belongs to G dash. So G inverse A, B, A inverse, B inverse B is equal to G dash B. Now it can be written as G dash A, B, A inverse, B inverse B is equal to G dash B. So G dash A, B, A inverse is B inverse B को लिख दिया हमने E is equal to G dash B. Now it will be written as G dash A, B, A inverse is equal to G dash B. So G dash A, B, A inverse A is equal to G dash B A. G dash A, B, A inverse A is equal to G dash B A. So G dash A, B, E is equal to G dash B A. Then G dash A dot G dash B is equal to G dash B dot G dash A. So G dash is a normal subgroup, and so product of two right coset is again a right coset. Hence G by G dash is a abelian. If order of G is equal to P square, where P is prime number, then order of G is abelian group. So इसका प्रूफ देखते हैं. Let Z be the center of G. In order to prove that G is abelian, we shall prove that Z is equal to G. Since P is prime number, therefore by a theorem Z is not equal to E. Therefore order of Z is greater than 1. But Z is subgroup of G. Therefore order of Z must be divisor of OG. OG must be divisor of P square. Since P is prime, therefore either order of Z is equal to P or P square. If order of Z is equal to P square, then Z equal to G, it complete the proof. Now suppose that order of Z is equal to P, then order of z is less than order of g because p is less than p square. Therefore, there must be an element which is in G but which is not in Z. Let A belongs to G and A does not belongs to Z. Now NA is a subgroup of G and A belongs to NA. Also, X belongs to Z implies that XA is equal to AX and X belongs to NA. Thus, Z is a subset of NA. Thus, Z is a subset of NA since A does not belongs to Z. Therefore, the number of element in NA is greater than P. But order of Na must be divisor of P square. Therefore, order of Na must be equal to P square. Then Na is equal to G. Therefore, A belongs to Z. Thus, we get a contradiction. Therefore, it is no possibility that order of Z is equal to P. Hence, order of Z is equal to P square, which is equal to Z, which is equal to G. Hence, G is abelian. Now, there is another theorem. Let Z be the center of a group G. If G by Z is cyclic, show that G is abelian. Proof. Let Zg be a generator of cyclic group G by Z for some G belongs to G. Let A comma B belongs to G. Then AB is equal to BA. Since A belongs to G and ZA belongs to G by Z, but G by Z is cyclic group generated by ZG. हमने साइक्लिक ग्रुप की डेफिनेशन देखी थी. अ ग्रुप जी इज साइक्लिक इफ फॉर सम ए बिलोंग्स टू जी every x belongs to G is of the form a to the power n where n is some integer. Therefore, there exists an integer m such that ZA is equal to ZG to the power m is equal to ZG to the power m. By definition of coset, A belongs to ZA. So A belongs to ZG to the power m. Since ZA is equal to ZG to the power m, there exists Z1 which belongs to Z such that A is equal to Z1 G to the power m, B is equal to Z2 G to the power n. Since Z2 belongs to Z and n is any integer, AB is equal to Z1 G to the power m and Z2 G to the power n. So it can be written as Z1 G to the power m and Z2 G to the power n. Here Z1, Z2, G to the power m and G to the power n. Since Z2 belongs to Z and Z2 G to the power m is equal to G to the power m Z2. So it can be here Z1, Z2, G to the power m plus n. Again, BA is equal to Z1, Z2, G to the power n, G to the power m. So Z2, Z1, G, m plus n. So AB is equal to BA for all A comma B belongs to G. Hence, G is abelian. और यही हमें प्रूफ करना था.